like the set of tools that we're gonna learn in this chapter is actually very essential in many other topics, not just for this, which is like all as a part of from linear algebra, an essential part of linear algebra, which is called matrices. The idea is to turn higher order differential equations into a system of first order differential equations. So if we have a higher level, like second, third, fourth, whatever, even like more than one equation from higher order but they are coupled, then it's better to turn them into a system of first order, where these systems can be like every time we're talking about a mass spring number system, one single mass spring number system. But in fact, if you want to model the four wheels, you don't model every one separate, because what happens in one wheel will affect the other. So they will be coupled somehow. They will be like kind of 4 second order differential equations. On solving one, you have to solve the other, or assume something about the other. So solving every one independently is a solution, but it's not the most correct solution. It's better if we can blind all of them in one system and then solve all the system together. This is one thing. Like actually most of the systems are like this. Like if you're modeling the like a robotic arm, for example, that has multiple joints, like modeling every joint alone is not again the best situation that you can do, but you have to model all the joints together, because the movement here affect the movement in the other joints. So like also if you wanna model like a quadrotor, like the drones, in order to model it correctly, you need at least a differential equation from the 6th order, because it has 6 degrees of freedom. You have velocity in that direction, velocity in that direction, velocity in that direction. Those are the 3 velocities. You have the orientation. The quad can do like this, can do like this, and can do like this. Those are another 3 degree of freedom. So those are 6 degree of freedoms. In order to write one dynamical equation for this, you need a 6th order differential equation. No one can solve that. There's no even mathematical tools that can find the roots of 6 orders. So what they do, they turn this higher order into a state space, or a 6 first order differential equations. And then they solve them using this. In fact, most of the dynamical systems are turned into this chapter. Like literally, most of the, particularly if you do things engineering-wise, they turn them into system of first orders, and then they solve them using matrices. So what does a system look like? It might look like this. Just differential equations that maybe dx by dt or dx1 by dt equal x1 plus x2 plus x3. dx2, sorry, this is by dt. By dt equal x1 minus 2x2 plus 3x3. dx3 by dt equal x1 minus x3. This is a system, or as an example of a system of first order differential equations. Why here we call it system? Because they are coupled. Like the first equation depending on the second equation and third, the second variable and third variable. The second one depending on the second and the 3 of them. The third one depending on the first and the second. So like there is evolution, but those differential equations, they don't work separately. They work according to the other differential equations as well. So solving this, but as this is not very easy, we have to find a tool that give us like the collective information about this. Okay? We can turn this into a third order differential equation in one variable. That can be done, but that's not the best. So one way we could reorganize them as you guys were doing in numerical. Remember the system of linear equations? Who did not do numerical methods? You guys are which department? Oh, chemical they don't do numerical.
It's
We did linear algebra.
Oh, you did linear algebra? They didn't do
Numerical.
linear algebra, they didn't do anything. They are chemical.
numerical is supposed to be taken for us in the 4th year. So, sorry, yeah, 3rd year.
Why? Okay, that's politics. Let's just keep here. It's, well, we can, like suppose that none of you heard about these before, we can reorganize this or write this in a way that looks much better and much organized than this by introducing what we call matrices and vectors. So we're gonna write this as, like this could be written first as x dot, x1 dot, x2 dot, x3 dot. Dot means dx by dt, okay? So we can write this as one vector like this equal a matrix times another vector. We can reorganize these in here. How is that? We just here, this is a vector of x1 dot, x2 dot, x3 dot. Here x1, x2, x3. And here are the numbers. We're gonna organize the numbers that connect these systems together. بمعنى, this x1 will equal whatever we have here times whatever we have here. So we're gonna put the numbers here, that if we multiply them, this number times this number times this number times this, it's gonna give me the first equation, which would be, we need 1 of x1, 1 of x2, 1 of x3. Like this is, you can illustrate it, if you multiply this, we call this row, times this column. You multiply the first element times the first element, the second element times the second element, third element times the third element, and this will give you this element here, which is this equation. We can do the other equations exactly the same. So it will be 1, negative 2, 1, negative 2, and 3. And then what about the third one?
1, 0, minus 1.
1, 0, minus 1. Why 0? Because there is no x2, because 0 times x2 is 0, so there will be no x2. So this system here now can be written as this. Well, that's more organized. It's not only that. We can even have a notion that we're going to talk about, which is matrices and vectors. We can call this, all of this, as big X dot equal. We can call this as A matrix. We can call this as X. It's the same X, but it's dot. So this system, or this group of differential equations, can be written as this. The good thing about that, it's, if this is like 100 by 100, if you have 100 equations, they're gonna be again exactly the same thing. It doesn't really matter, but we know just that this X is like 100 vector. This is a vector with 100 elements. This is a matrix that 100 times 100. But we can somehow reorganize them in a much better and more organized way in these new things which we call matrices and vectors. Okay, so is it a matter of just organization? Is it like these matrices help us just to rewrite them in a better way? No, it's much more than that. These new things that we introduce, which is matrices, they have algebra and mathematics خاصة بيهم هم. They have their own mathematics that can actually help us to solve this system, even if this is 100 times 100. It's just like we deal with it as elements now. It doesn't really matter Like if you're adding 1 plus 1, is it the same concept as if you're adding million plus a million? It's the same concept of addition. That's exactly the same here. If this is a 2 by 2 matrix or a 100 by 100 matrix, it's the same concept. So the first thing that we can turn a system of differential equation into matrices, and then we can deal later with these matrices. And we said last time that we can even turn any higher order into a system. Like any higher order differential equation, we can turn it into a system, then system into matrices, then we solve this system now. And this will be like what we're gonna learn in this chapter. Okay. So, but before that, we need to learn about like some of the algebra and some of the mathematics that related to the matrices themselves. So as I said last time, for now, let's just have the mental picture of a matrix in our brain, in our brain as a storage device. It's literally like this class where we have, this is one spot that we can put a student or a bag or whatever. It's just something that we can store it there and take it back. It's exactly, the matrices are like this. We stored the information of this system into this matrix. What I mean by the information? The information is that how x1, x2, x3 are connected together. This information is all embedded here, not here and there. Actually, this and this is just always like this. It's always x1 dot x2 dot x3 dot until xn, and this is x1, x2, x3 until xn. So there is no new information in here and there. Everything becomes in this matrix. And they call it the dynamical matrix. So it's just one matrix that contains all the information that you need to know about this system. So, matrices for us are a storage devices where we can access these elements. Not just that, we can actually do operations and these numbers inside work together in a very nice harmony. It's not just like storage. No, storage in a specific way that when you do operations, you preserve the information contained inside this matrix. So we have like variety of these matrices. We can have them as one column, 1, 2, 3. We can have them as rows, 0, 1, minus 1, 2, 3. We can have them, this is 3. We can call it as one column, but it has 3 rows. So this is 3 times 1. This is 1, 2, 3, 4, 5. So it's 1 times 5. It's not multiplied. Okay? It means this is the number of rows, this is the number of columns. Okay? We can have them as 1, 0, 2, 5. This is how many rows and how many columns? 2 by 2. It is not 4. Yes, it contains 4 elements, but it's 2 by 2. It means 2 rows and 2 columns. So we can have them as A11, A12, A13, A21, A22, A23, A31, A32, A33. Just as generic as this is a 3 by 3, this A, 3 by 3 matrix, that it has 3 rows and 3 columns, and the element here, we just give it a name as A11, the element in first row and in second, in the first row and first column, first row, first column, first row, second column, first row, third column, and then second row, first column, and so on. And then we can have them again like different dimensions. Is you can just make your own 1, 2, 3, 5, 0, minus 1, This is 3 columns, 3 rows, 2 columns. So 3 times 2. Okay. So these are like, now imagine that we are building a new mathematical framework that its elements are matrices. Zaman, we have like this mathematical framework that all the elements here are numbers, the real numbers. So we collected all the real numbers and put them here. So the elements were just numbers. Any one of these were just numbers. And we were doing operations here. We were doing addition, subtraction, multiplication. Inside this, 2 times 2 is 4, 2 plus 2 is 4, 1 times 0 is 0. All these operations were happening here, and the outcome of any 2 operations is one of the elements inside. So it's self-contained. You're not generating a number that it's outside. That's exactly what we're gonna do for the matrices. So we're gonna have the matrix platform where all the elements here are matrices. All sorts of matrices that you can imagine, they will be here. We need to define addition operation, subtraction, multiplication, and some properties. Well, what are the 2 important properties? Here, we had a very important element, which is the 0, the addition identity. The 0 is such an important number because 0 plus any number is the same number. And we have the 1. What is the importance of the 1? It's the multiplicative identity. 1 times any number is the same number. We have to have those 2 elements in any mathematical constructions, by the way. It will not be complete if you don't have those. Those are like the most important 2 elements in any mathematical constructions. The multiplicative identity and the additive identity. So we have to have them here. We have to have like the matrix that act as 0, which is just a matrix filled of zeros. And the identity matrix, we call it I. What do you think, what would be the I look like? Sorry?
Ones.
No. It's
Ones in the ring.
a diagonal matrix which has ones here, zeros everywhere else. This is called the identity matrix. We're gonna talk about it, for sure. So we now, like today's lecture, we're gonna talk about that mathematical construction, which is matrices. Matrices are elements, they're elements, like it's a mathematical constructions where the elements are matrices, and the operations will be happening over matrices, and the result will be a matrix. Multiplying 2 matrices is another matrix. Adding 2 matrices is another matrix. So as we were learning in all like primary school and what is the
Secondary school.
yeah, primary and secondary school in addition, multiplication, blah blah blah. We can do all of this here. Even integration, differentiation, and all of that. There is integration and differentiation here. So there is like a complete framework of mathematics that can be applied here. There is actually a very great book that it's like almost 2,000 pages. It's called Matrix Mathematics. It has only the theorems and the results without any proof, because they took the proof out, that were obtained in all the matrices, on all like these constructions. It's almost 2,000 pages.
Doctor, without proofs, 2000?
Yeah, it's actually, it's one of the most useful field that mathematics invented for everyone. Like all these machine learning terminologies are actually running because of these matrices operation. Anyone knows what is GPU?
Graphics processor unit.
Yeah, the graphical processing unit, or the graphic cards in your computer, the GPUs. People in computer science should know that. Like, it's just more than just graphical now. all these machine learning and ChatGPTs and all these like heavy computation that happens, that produces all these smart systems, they are enabled because they invented this GPUs. GPUs has a lot of cores. You know that when you buy a computer, it's i7 and i9, and those are the number of cores in your CPU. It has 9 cores. Cores are like a unit of computation, or like, well, it's not exactly, but you could consider it like that. So when you buy a laptop, your laptop, this might be an i9 or i7. It has 7 cores. The GPU, anyone has like interested in gaming or have a GPU at home that does gaming?
Yes.
Only one?
Yes.
Why you guys are shy? Like I do have 2. It's you have to have them. Like the for example the 4090, which is the least that was produced now. Well, Nvidia announced a new generation last week, but the biggest that in the market now that you can find in Qatar, it's something called 4090.
RTX.
Sorry?
RTX series?
Yeah, RTX series. That's the highest in RTX series, which is the highest in the like kind of commercial ones. There's actually they're much bigger than these, but those are not for public use. They're used for like professionals for doing some machine learning tasks. But this one, like the maximum that you can get in the market for the CPU is 9 cores. I guess there's not more than i9 now.
CPU or the GPU?
CPU. Well, CPU is i9. There's i11 that I guess start to count. So it has 11 cores. How many cores in the RTX?
4090.
RTX 4090. Anyone knows how many cores in here? Give a number.
50,000?
15 million.
It has 16,000 core. And you can imagine like how much computation this can do compared to the most powerful CPU computer that we have. Well, this is not a right comparison because the cores in the CPU are much bigger. The cores in the GPU are smaller. However, it's well enabled because they can do matrix multiplications or matrix operations very, very fast. So they do what they call parallelization. They do computation. The difference between CPUs and GPUs, the CPUs takes the processing one by one in a serial manner. So they take one operation, do it quickly, the second operation do it quickly, very, very quick. But the GPUs does the computation in parallel. They do like bunch of computation together. And that's why they're very, very fast in the small operations, which all these machine learning and platforms are running on doing billions and billions of small operations. What enables that is matrices. Because you can organize things in these like flexible framework that has, it's just the dimension is just a number. So, well, I can keep talking about these matrices like for ages. But for us, in this chapter or in this course, we need to know, well, like that's why like everyone should study linear algebra. I don't know why linear algebra is only studied by like few departments here. This is wrong. This is certainly wrong. Linear algebra is an essential subject where you study actually more. Like there's a big chapter or like more than one chapter about matrices. So we need to learn some very basic operations about matrices. How to add 2 matrices, for example. How to subtract them and how to multiply them. And what is I, the identity, and what is the zero. Okay, those are the things that we're gonna learn. Very, very easy things. Okay. Well, can we add any 2 matrices?
It should be the same size.
Yeah, they should be at the same size. So that's a restriction that we didn't know before. Before we can add any 2 numbers or subtract any 2 numbers. Now we have something like structure. So the A and B can be added and subtracted only if they are from the same size. Must be same size. What I mean by same size, the number of rows equal the number of rows, number of columns equal the number of columns. So for example, 1, 2, 0, 3, minus 1, minus 2, plus 0, 1, 2, 3, 4, 5. Can we add those two matrices?
Yes.
Yes. Why? Because it's 3 times 2, 3 times 2. Okay? So it is not because everyone has 6 elements. No, it has to be exactly the same shape. So how to add them? It's gonna give us a matrix from the same shape as well. We add the first number to the first number, the second number to the second number, and so on. I guess that's very obvious. So 1 plus 0 is 1, 3, 0 plus 2 is 2, 3 plus 3 is 6, minus 1 plus 4 is 3, minus 2 plus 5 is 3. Subtraction is exactly the same. So the only thing that you need to know is that they must be from the same size. Zero, 1, 2, 3, plus 3, 2. Plus 0, 2, 1, 3, 5, 2. Can we add those two matrices?
No.
No, we can't. Even this is like 3 by 2, this is 2 by 3. But they cannot be added. They are still 6 elements and 6 elements, but they are not the same size. It's just like this will be added to this, and then what happens? Then this will be added. What happens to this one? No. So this cannot be added. They have to be exactly the same shape. The zero matrix, since we're talking about addition, it's just a matrix with all zeros. 0, 0, 0, 0, 0, 0, 0, 0, 0. It could have like 0, 0, 0. Like whatever dimension you want, it's just a field of 0. Because if you added this to any 1, 2, 3, you just add elements by elements, it's gonna give you the same matrix again. The identity, so, okay. There are a specific type of matrices is called square matrices. A square matrix is n by n. N by n means the number of rows equal the number of columns. This matrix has a lot of things that we're gonna deal with it later. Okay? So a square matrix is the number of rows equal the number of columns. مصفوفة مربعة يعني طولها زي عرضها. Okay. So an identity matrix has to be a square matrix. Identity matrix has to be a square matrix. And its elements is always like this. 1, 1, 1, 0, 0, 0. this one time. 0, 0, 0, 0. So this is called the main diagonal, not this one because it has two diagonals. This one is called the main diagonal. The main diagonal is ones, and the rest are zeros. We call this the identity matrix. You cannot have an identity matrix that is not square. Any identity matrix has to be square. Okay? This will have like a very important rule later in the things that we're gonna do, the identity matrix. But since we're talking about identity matrix, how we do multiplication in matrices. So we need, suppose that we have A as 2 by 2 matrix, 1, 0, 2, 3. B is 3, 2, 0, 2, 3, 4. C C 0, 2, 1, 2, 3, 5. I don't care about the numbers, I'm just making the number. The number doesn't mean anything for us. We're talking about the structure itself. Now, how we multiply A times B?
You can.
Well, actually, can we always do the multiplication? No. So, in order to multiply any two matrices, x times y, a matrix x times matrix y, for this to be valid, this has to be n times m, like the dimension. If the dimension of the first one is m times n, the second must be m times anything else. It could be n or it could be any other number, but the important part is that this number has to equal this number. The number of columns in the first matrix has always to equal the number of rows of the second matrix. This is like a must condition. We cannot perform the multiplication if this condition is not true. So the numbers of columns in here, which is the second number here, must equal the number of rows in the second. Then we can perform the multiplication. And what would be the result? A matrix that has those two numbers. It's n times r. Okay? Alright, so let's check. Can we multiply A times B in this case? What is A?
2 by
2 by 2. What is B? 3 by 2. What is C? 2 by 3. Okay, so now A, we said it's 2 by 2. B is 3 by 2. Can we do this multiplication?
No.
No. Why? This number does not equal this number. So we can't do this multiplication. We can't do the multiplication. It's not valid. Okay. Can we do B times A?
Yes.
Oh, like we can. This is completely now different from what we learned in high school or in like 2 times 3 is 3 times 2, and it's always there. Here, you could even have one that it's doable, the other one is not doable at all. So B times A, why? Because B is 3 times 2, and this one is 2 by 2. So those two numbers are equal, then we can do the operation. What would be the result?
3 by 2.
Another matrix, which is dimension is 3 by 2. We don't know yet how to generate these numbers. Okay? We're gonna talk about this later, but we talking about is the multiplication possible or not? So it's only possible if this number equal this number. So here it's not because this is 2 and 3, so they're not. We cannot multiply these. But here we can. Even this is A times B, this is B times A. This one is doable, this one is not doable. Okay, what about B and C? Let's see B times C. What is B? 3 times 2. What is C? 2 times 3. Is this doable? Okay. What is the result?
3 by 3.
3 by 3. Now, what is C times B? Is it doable? What is C?
2 by 2. Oh.
C is 2 by 3. What is B? 3 by 2. Is it doable? Yes. But what is the result?
2 by 2.
2 by 2. So see, you can see like things that are here, again, completely different from what we knew before. Now, B times C is doable. C times B is doable, but they has nothing to do with each other. They are not equal. They're not related at all. In any case, by the way, even if this, the same dimension as this, there's gonna be completely two different matrices. And this, they call this as the matrix multiplication is not commute. الكوميوتيشن ريليشن شيب اللي هي 2 تايمز 3 هي 3 times 2. You can replace the multiplication.
Order matters.
In matrices, no, they don't commute. A times B has nothing to do with B times A in all type of matrices. Okay, but now let's learn how to perform the multiplication. Let's take one that is doable. I guess we said that B times A is doable. So B, what was B? 303. 224. Now we're gonna multiply this times A. Which was 1023. 1023. This is, we said that this is 3 times 2, this is 2 times 2, then the multiplication is possible. And we're expecting to have a matrix 3 by 2. So it has one element, three rows. So it has one element here, 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 one element here. That's what our expectation. We need to generate those elements. What are inside these boxes? All right. So the matrix multiplication happens that you take this. This was 2, right? This. The matrix multiplication happens that you take this row. No, it's not multiply 3. Times this column. You multiply row times column, element by element, and then add them, and the addition will be here. يعني 3 times 1, 3. So I'll make them 3 here. Plus 2 times 2 is 4. So this result here will be this row times this column, element by element, and then you add them. The result will be here. Similarly, what do you expect? How we generate this number? Exactly. What is this? What is the location of this? First row, first column. So it's gonna come from the first row, first column. What is the location of this? First row, second column. It's gonna come from the first row and second column. So you're gonna multiply this times this. The result will be here, which will be 3 times 0. So it's 0 plus 6. Now, this element here, this is in the second row, first column. So we're gonna take the second row, multiplied with the first column. 0 times 1 is 0. 2 times 2 is 4. And then the same row times the second column, so 0 times 0, and then 0 plus 6. And then the last two elements coming from this row times the second, the two other columns. So 3 times 1 is 3 plus 8, because this times this. And then the same row times this, so 0 plus 12. Which would equal to 7, 6, 4, 6, 11, 12. And this is how we do the multiplication. So the first thing that we need to know is that the multiplication has to satisfy this property. What's that? Yes, this property. And then we multiply like columns times rows, columns times rows, column times rows, in order to populate the other matrix. Populate it means like generate the numbers in here. Well, since we're talking about multiplication, we should talk about division. Because multiplication, like addition and subtractions are the same operations but with different sign. Multiplication and division are actually the same. But can we do division in matrices? No. We don't actually have a division in matrices. We have something that it's kind of, you could manipulate it as division, but it's not division.
Times them.
So we don't have A divided by B. You don't see that in matrices at all. But you could have A times B inverse. So we have to define the notion of inverse as well. What is an inverse of a matrix? Well, first of all, only square matrices has an inverse. So you cannot invert non-square matrices. What is square matrices again?
And by
And by n, matrices that has same rows and same columns. So for a matrix to have an inverse, number one condition, it has to be square. Is that the only condition? People who studied linear algebra?
No, the determinant should not equal 3.
Exactly, the determinant. Oh, again, another new thing that we need to learn, which is something called the determinant. For every square matrix, again, for every square matrix, there is something called det A, or sometimes it's written as this, determinant of A. And this value, we're gonna learn how to do it quickly. But for a matrix, A to be invertible, like we can generate A inverse, two conditions has to satisfy. A has to be square, like n by n. Two, det A has not to equal 0. Okay? So for any matrix A, in order to be able to find the A inverse, which is like equivalent to division-ish, in order to find that, then two conditions have to be satisfied first. Number one, A has to be square, that's for sure. Two, the determinant of A has not to equal to 0. So what is the determinant? Again, the determinant only for square matrices. So if A, for example, is 1, 2, 3, 0, what will be the determinant? We did this before actually in the variation of parameter method.
1 times 0 plus.
Exactly, you multiply this times this minus this times this. So it's 1 times 0 minus 2 times 3, which is negative 6. So can we have inverse for this matrix?
Yes.
Yes, it's not 0, so, and it's squared, so we can have the inverse of this matrix. That's easy. How to find the inverse, that's another story. But what if A is 3 by 3? A11, A12, A13, A21, A22, A23, A31, A32, A33. How to find det A or determinant of A?
لازم نحط
Doctor, there's I think 3 methods.
No, there's only one.
No, there's 2 methods.
There's
3
one.
by 3, yes.
There's one. فكرة إن أنت تاخد التو كولومز هنا وتحطه وتعمل كده ده شوية دجل بيعملوهم الجماعة اللي مالهمش في الماثematics، بس this is not a method. Okay? The only method that it's known, it's based on something called permutation. It has a root, it has a meaning in terms of the proofs. The other method is just like kind of, remember when you watch the videos that if you want to multiply 1 times 9, you take this first digit and combine it with this first digit and do like that. This is like just kind
It's
of.
not mathematically proven.
It's not about mathematically proven. It's correct, but it is not a method that you're gonna gain anything from it. Like here, any determinant has to be converted into 2 by 2. So we're gonna convert this into 3 2 by 2. And we know that 2 by 2 is given like this. 2 by 2 always multiply this number times this number minus this number times this number. That's it for the 2 by 2. For any other matrix, you need to keep taking, you can turn this into 3 2 by 2 and then do every 2 by 2 again and add them in a specific way. What if this is 4 by 4? No, you have to turn it into 4 3 by 3. And every 3 by 3 has to be turned into 3 2 by 2. It's very, very long. But for us, like we will, like most of the time, we'll be dealing with this guy, 2 by 2. Just 2 by 2. Or we're gonna learn how to do it for the 3 by 3 as well. In order to find the determinant, you can use any row or any column. Choose any row or any column. Well, since we don't have a big preference, so I'll just pick the first row. I could pick any other row or any other column. And I say A11, take this element. Imagine that you eliminate its row and its column. Imagine you eliminate, so now we're focusing on this element now.
Yes.
Yes.
Is that like the cross product of two?
Yes, the cross product is finding the multiplication, finding the determinant-ish. But in the cross product, you always use the first row, which is ijk, in order to find what is the dimension in that, what is the dimension in that, what is the dimension in that, or what's the amplitude in the direction of I, the direction of j, direction of. So you take this element, you imagine that you don't have these, and then you take what's left. So it's A11, what's left?
A22, A23, A32,
A23, A32, A3. Then minus, there is always something called the sign rule. This is always positive, negative, positive. This leading element is always positive. Even if you decided to use this row, yeah, plus, negative, plus, negative. So you start with positive and then you go negative, plus, and so on. So, negative, this number, which is A12, what's left?
2, 1.
So, we're gonna imagine that we're gonna eliminate this row and this column. So it's A21, 2, 3, 3, 1. هو الديترمنت هو حاجة واحدة بتتحسب في كل الدنيا، هو determinant. It's in anywhere. Plus again the last element, which is A13,
2, 1, 2.
again this and this, so it's A21, A22, A1, 3. And then now it become like the 3 by 3 become 3 2 by 2. We calculate this, we know multiply this times this minus this times this, and then the result you multiply by A11. You generate a number here. Minus, you generate a number here, plus, you generate a number here, you add those three numbers, you get the determinant. Let's do this in a matrix. Oh, it's not, it's 10 already. 1, 0, 2, 3, 4, 2, 1, 0, 2, and 0, 3. How to find the determinant here? So I'm gonna use this first row. So it's 1 times
4, 2.
4, 2, 0, 3 minus 0 times whatever. I don't need to write that because 0 times anything will be 0 plus 2 times
3, 4, 1, 2.
4, 3, 4, 1, 0. And then this times this, which is 4 times 3 is 12 minus 0. So 1 times 12 this is 0, so minus 0 plus 2 times 0 minus 4. So it's 12 minus 8, which is, I guess, 4. So the determinant of A is 4. Sorry? Okay, so this is how we calculate the determinant. Why we need the determinant? Oh, well, the determinant is used in a lot of other things, but for us, is that, like, to find the A inverse, we have to satisfy two conditions. Square that A should not equal to 0. So this matrix has a determinant. Has an inverse, because its determinant is not 0. Okay? So next time we're gonna talk about, inshallah, next lecture we're gonna talk about, like, continue, like, for some time in doing some algebra, and then we're gonna see how we're gonna do something very important, which is called the eigenvalues and eigenvectors. Because those are the main things that we're gonna use in differential equations today. The eigenvalues of A, the eigenvalues of the eigenvalues and eigenvectors of F.
دكتور هذا الشابتر قبل الأخير صح؟
Yes. The chapter الأخير we're gonna finish it in 1 week, so it's not a big deal. Hopefully, inshallah, we're gonna finish before the like